Okay, so now we'll get going. Short introduction.
Yeah. So yeah, we have some technical issues, but glad that we have get the solved. Okay, let me be great. Okay. Professor Spearot was Wolverine, welcome home, and he has received many prestigious awards, including the Rothko Junior Faculty Enhancement Award in 2007, NSF Career Award in 2010, the TMS Young Leader Professional Development Award in 2010 also, and Young Leader International Scholar Award in 2012, and MPMD Distinguished Service Award 2020, and many more. And Professor Spearot is also known for his consistent dedication to teaching and education. At the University of Arkansas, he was a recipient of the Most Outstanding Teacher, the John Imhoff College of Engineering Outstanding Teaching Award, and the Arkansas Alumni Association Rising Teaching Award. And at the University of Florida, he has been named Teacher of the Year. So with that, please join me in welcoming Professor Spearot to give his talk today.
Thank you. Thank you. Thank you. I apologize for the technical difficulties there, which apparently my laptop just decided to totally lock up. So fortunately, I have my slides on basically USB key, and so we're going to use this one here. Again, as basically UA said, my name is Doug Spearot. I'm a professor at the University of Florida, and what I'm going to talk to you about today is the idea of mesoscale modeling of plasticity in actual metallic materials via advancement of what's known as the discrete dislocation dynamics simulation method. So this is a mesoscale simulation method, as I'll talk about, that kind of fits between atomistic level actual calculations and say finite element level type of work. The work that I'm going to show today is primarily from the actual PhD dissertation of Dr. Darshan Bamni, who was a PhD student in the Material Science and Engineering Department at UF, and he's currently a postdoc at Los Alamos National Laboratories. Oops, that's not going to advance the slides. Oh, well, I'll have to stand over here. Why will the slides advance? There we go. Okay. Let me see if I can still get this to work. But basically, I'm a graduate at the University of Michigan, so it's good to be home. I'm there. It's been probably about 8 years since I was here last, and then I graduated in the spring of basically '99. So I was the president of the Pi Tau Sigma chapter at the time here during the actual 1998 school year. These very old, yellowy, dated actual photographs, non-digital photographs from basically commencement, the actual university commencement from spring of 1999. So it's good to be home, and I'm really happy to kind of be here and get an opportunity to essentially give a presentation today. So ultimately, what I'm going to be talking about is the idea of plasticity in actual polycrystalline metals, and this is a problem that we're trying to work on from a mesoscale perspective. And so this idea of plasticity in polycrystalline metals is governed by the individual and collective behaviors of dislocations and actual grain boundaries. And so I'll talk a little bit more about what those are as we go through the actual seminar on there. But ultimately, there are a lot of examples experimentally on how these individual mechanisms are essentially important. And so people have used experiments to identify the nucleation of actual dislocations from an individual grain boundary or essentially within a grain. This is typically a stress relaxation process in terms of the actual nucleation of the dislocation. People have used lots of different actual microscopy techniques to look at the network or the created network of dislocations within a metallic material. This leads to basically changes in the yield strength or the strain hardening associated with the material. And then ultimately, one that's going to be important for what we're talking about today is people have used, again, basically microscopy, different types of actual microscopy techniques to understand dislocation grain boundary interactions, at least look at individual actual grain boundary interactions. Again, this influenced the yield strength and the strain hardening associated with the material. And so ultimately, studying dislocation motion and dislocation grain boundary interactions is critical for understanding the microstructural basis for basically polycrystalline plasticity. What's going on at the microstructure level that influences the macroscopic behavior of our system. Now, this is an inherently multi-scale problem, essentially requiring modeling efforts at various length and time scales. on there. So if you create a fairly traditional time scale versus length scale type of plot, this tool that I'm going to talk about today, discrete dislocation dynamics simulations, falls in this kind of middle range here, where our length scales are typically on the low end of the micrometer type of scale, and our time scales typically range from nanoseconds to tens of microseconds, essentially. So this is kind of our wheelhouse in terms of length scale and time scale on there. Now, as we'll talk about in a minute, DDD explicitly simulates the dynamics and interactions of discrete dislocations. So we don't have atoms anymore, but we have dislocations that are essentially the entity that we're going to try to simulate. Again, length scales here, time scales here, and ultimately it requires input from things like atomistic simulations to define some of the physics with regard to how dislocations essentially move. So this is some work from actual molecular dynamics simulations where we're looking at the nucleation of dislocations from an individual grain boundary. Things like mobility laws or the mechanical structure of a grain boundary are important as inputs at this mesoscale. And then ultimately the outputs of our mesoscale here are things like dislocation density evolution laws, so how the network evolves with an actual mechanical loading, or things like hardening coefficients. And those are important inputs to things like crystal plasticity on here. Now, ultimately, we have to make a lot of decisions here. We need to make a lot of decisions with, for example, how dislocations, say, pile up at an interface or some boundary, essentially, in the system, because these decisions impact things like the stress strain response. It impacts the actual macroscopic response. But with this DDD tool, we can understand these type of correlations between the microstructure of the material and the macroscopic actual type of behavior. So it kind of fits as this bridge between atomistics and continuum plasticity. Now, DDD basically requires models derived from theory or atomistics or experiments to describe the actual dislocation behavior on there. Two of which that are particularly important are the idea of the kinetics of the dislocation. So what is the mobility of a dislocation under a given shear stress? So typically a linear relationship between dislocation velocity and driving force is often assumed. But if you do atomistic simulations and you try to examine what is the velocity of a dislocation as a function of the stress applied on that dislocation, you certainly do not get an actual linear behavior. It's linear for a brief period, which is typically known as a phonon damping regime. But if you're interested in the fast motion of dislocation, say under high loading rates or shock type of actual, basically type of behaviors, we need to account for the full nonlinear description of how dislocations move essentially within our system. And so this type of information can be provided from atomistics to actual discrete dislocation dynamics. In addition, one of the kind of open available opportunities with regard to discrete dislocation dynamics is incorporating interfaces on here. So understanding dislocation grain boundary interactions is often ignored or totally neglected, essentially, in discrete dislocation dynamics. And so this is some work by basically Zhou and Lassar a number of years ago, where they created a actual polycrystal made up of a whole bunch of square, basically, domains on there. And they basically allowed, in one case, the dislocations to propagate through the individual domains with very low resistance. And in the other case, they have totally impenetrable interfaces. And they tried to look at the difference between the mechanical, basically, response of one system versus the other. But this is a very toy model, and we essentially want to be able to incorporate realistic, basically, grain boundary structures. So modeling polycrystalline plasticity using DDD requires these physically representative models for describing dislocations and dislocation other defects type of actual phenomena. So what I'm going to talk about today is basically this idea. We want to develop and implement physically representative models for dislocations and dislocation grain boundary behaviors within DDD, and we want to leverage these advancements to obtain mesoscale insight into plasticity in metals. Now, what we basically done, what my student Darshan essentially did, is he did four things. He first improved the description of dislocation mobility using MD simulation data. He introduced a framework to model the mechanical structure of grain boundaries and implement that within discrete dislocation dynamic simulations. He introduced a model to describe the evolution of the grain boundary structure due to the interaction history. And this is the really important part, not just one dislocation, but what happens to the structure of the interface as many dislocations pass through it. And then finally, we want to be able to validate our simulations. And so to do that, we need to develop tools that allow us to make a link to what experimentalists can actually measure. And one of the things that basically experimentalists can actually measure is the idea of diffraction patterns. And so we've been developing virtual characterization tools and specifically diffraction-based tools to extract information on our actual microstructure. I'm not going to talk about this one today at all, but I am going to touch on these other three essentially in this presentation in terms of the grain boundary dislocation interaction problem and developing some of these type of tools very briefly at the end of the presentation. All right, so for those that are not familiar with the idea of discrete dislocation dynamics, it essentially has an iterative type of time step actual process. And so the first thing that we have is we have the discretization of the dislocation network. Essentially what we're doing in discrete dislocation dynamics is we are modeling dislocation lines and we're discretizing those dislocation lines into individual nodes connected by segments. And those segments so can have an actual line direction, and those segments can have an actual Burgers vector associated with them. Then what we want to do is we're going to calculate the forces acting on the nodes associated with the individual dislocation lines. And so we use a Peach-Kaler force type of actual basically approximation in order to actually measure that, where this total force here, pardon me, the actual total stress here is the sum of both external contributions, basically our applied loading, and internal contributions, where these internal contributions can come from dislocations. Other dislocations emit a stress field, and that stress field can influence some other segment essentially within the system. Or what's important for us is if our grain boundary or our interface has a stress field of its own, that'll all be incorporated into this basically sigma interface, probably sigma internal type of term. Once we have the force on our individual nodes, we can calculate the nodal velocity. So we have to define some sort of mobility law. This is where atomistic simulations essentially really helps us out. Once we have the velocity of the nodes, basically our nodes will move from their current positions to some sort of future position based on some magnitude of our time step. And we can measure the incremental area by which every segment of dislocation has essentially passed. And that allows us to calculate the increment of plastic strain that has occurred within our system. And from that increment of plastic strain, then we can back out the actual elastic strain, and we can measure the stresses that essentially resulted due to the motion of the dislocations essentially in our system. And then if our dislocations move, we need to consider dislocation interactions. And so two dislocations that used to be close to each other, but not directly interacting with each other, at least in a actual nodal sense on there, they may come really close to each other and they may essentially form different types of dislocations. We may have an actual reaction between two different dislocation types on there. So we need to account for all of these individual reactions. And so this would be one step, one actual iteration of the entire DDD process on there. And so we need information from atomistics here, we need information from atomistics here, and we need to understand at what resolution do we need to basically discretize the individual dislocation lines. All right, so now if we want to incorporate grain boundaries into this system, we need to consider models for the transmission of these actual lattice dislocations through individual grain boundaries. And we know from experiments and theory that this is going to be sensitive to crystallographic and structural details associated with the grain boundary. And so if we have a grain boundary and we have some dislocations that are approaching the grain boundary on an actual particular slip system, we can have direct transmission through the grain boundary on there, but this is relatively rare. More commonly, what we have is the idea of transmission of this dislocation with some sort of residual dislocation left over at the interface. And so we have a dislocation coming in, a dislocation that gets transmitted going out, and there is a leftover residual that sits on the plane of the actual grain boundary. So if we're going to model this, if we're going to incorporate this information into discrete dislocation dynamics, we have a couple of requirements. Computationally, we must be able to pass a dislocation nodes, the things that we are basically discretizing our dislocation lines with, across a grain boundary in space. So we need to be able to physically take one of these and move it across here. Second, we want to include the stress field associated with the grain boundary. The actual grain boundary has structure, usually has structure on there, and that structure provides a stress field that could be short range in some cases, but long range in other cases. So we want to be able to include the stress field. And then three, we want to consider how the grain boundary evolves as a result of multiple dislocation transmission processes. So how does this stress field change after the first dislocation, after the second dislocation, after the third dislocation, and so on, essentially. Now, these are all complicated things to do. So what I'm going to start with and show you today is we looked at symmetric tilt actual grain boundaries. Now, we can look at asymmetric systems and other types of systems, but there's a couple of unique things that we would have to add. So for simplicity, all I'm going to talk about today is actual symmetric tilt actual grain boundaries. Yeah. All right, so the first thing that we do is we implement a slip transmission algorithm. We want to be able to physically pass nodes from one grain to the next within our actual DDD simulation. So if you have kind of the schematic here, we've got the incoming grain and it has a particular slip system associated with it. We've got the grain boundary here. And so when our dislocation, our green dislocation, which is in the incoming plane, approaches the grain boundary, these nodes are initially stopped by the grain boundary. We need to define some favorable transmission outgoing, basically actual slip system. And we do this using traditional, basically geometry and stress criteria, basically the actual Lee, Robertson, and Birnbaum criteria here. This defines what slip system is our outgoing plane. But then we need to do the actual computational numerical part, essentially. So what we do is we construct a test embryo of our dislocation in our transmission grain here. And we introduce new dislocation content. We add the actual residual associated with the reaction going from green to red. Then we calculate the forces on these test nodes. And if the forces are actually pushing this dislocation away from the interface, we consider that favorable dissipation. The dislocation wants to propagate outward from there. And then ultimately we allow that to happen. If these forces were pushing back towards the grain boundary, then this nucleation, or probably this actual embryo here, is not favorable, and these red lines would just basically be reduced back to the interface, and the blue would essentially be eliminated. And at that point, the dislocation is just stuck, essentially. So this is our algorithm that we implemented into our discrete dislocation dynamics code to physically pass dislocations from one grain to the next. The second thing that we wanted to do is we wanted to include the stress field of the actual grain boundary on the ease at which this process essentially happens. And so we wanted to include the atomic scale structure of actual basically symmetric tilt grain boundaries. It causes this actual stress field here, and we want to be able to actually account for that. So we did some atomistic calculations. And so this is just one example, basically ground state actual grain boundary. This is a sigma 123 grain boundary. It's a 53.6 degree misorientation around a particular misorientation axis in pure aluminum. Okay. And at the ground state, you can see that the grain boundary has a structure, and it's got some sort of periodically repeating structure here. We can identify some regions of disruption associated with particular structural units. And if we use kind of an atomic measure of the state of stress, we can actually plot out on an atom by atom basis the distortion that is created by that grain boundary. This isn't exactly stress, it's in units of stress times volume, but essentially it's a measure of the stress field basically associated with this individual grain boundary. You can see that the stress field is essentially centered or basically emanates on these regions of basically disruption within the perfect grain boundary structure. And so these structural defects, or these changes in the structural defects, basically introduce these long range, basically actual stress fields. Now, the way that we're going to model this in our discrete dislocation dynamics code is we're going to use what's known as the disclination structural unit model on there. And so this is sometimes abbreviated as DSUM, and it employs a range of what are known as wedge disclination dipoles to model the actual stress field of the structure. So a disclination is essentially the analogy to a dislocation, but it's a rotational defect. So you can imagine a tube, and I make a slice through that tube, and I essentially open up that tube and wedge in an extra amount of material and then close that tube back together on there. And if I do that with appropriate crystallographic orientations, the tube itself will be perfect, but there'll be a stress field associated with the core along the axis of that tube. That's an actual wedge disclination. Now, unfortunately, disclinations by themselves have a divergent long-range displacement and stress fields. And so they actually have to appear as dipole or a quadrupole type of actual configurations. And so you need two of them. You need a positive wedge disclination and a negative wedge actual disclination. And there's typically an arm length associated with them. There's a distance associated with the two of them. And these will screen each other such that the stress field basically converges to zero as you go further away from the individual disclination. And so you can use these actual dipoles to describe the structure basically atomistically of our grain boundary. And so each of these individual defects, which are different from the rest of it, can be represented as an opening and a closing of the lattice because the actual orientation of the lattice changes at that particular location. And so this array of wedge disclination dipoles can be used to set up the initial stress field associated with our symmetric tilt grain boundary. All right, so we did some initial tests here. We've got basically two of our requirements. We've got our actual transmission algorithm and an initial basically grain boundary structure. And so we did some initial tests. We picked a random high angle grain boundary. This is a sigma 627 grain boundary. It's at 32.47 degrees. We have an incoming slip system. We have a dislocation loop size, and we have a magnitude of Schmidt stress basically that is driving that loop. And so this is our DDD models. It just has an initial singular loop in it for these initial tests. And if we look at the case where I have no grain boundary stress field, so I've got a grain boundary, it's essentially a geometric plane in my system on there. There's basically two of them on there, but I have no stress fields associated with that. My actual loop will open up and it will just get blocked by that grain boundary. But if I have stress fields here, so I actually have a stress field description of this plane, and here what happens is now for the exact same Schmidt stress, I can get transmission. And I can get a new dislocation in the new grain, that's the red line here, and I can form the residual dislocation between the green and the red that exists at the grain boundary plane. So that means that the presence of the grain boundary stress fields actually lowers the critical stress necessary for transmitting the dislocation from one grain to the next. So we'll dive much more into this as we continue in the presentation. We can do the math on this. And so this is our incoming slip system. This is our outgoing slip system. And so this is the Berger's vector and the character of the dislocation that sits on the grain boundary essentially. So it's very non-standard, of course. All right, so what we find is the dislocation transmission occurs at the glide and the glide of actual residual dislocations is strongly aligned with the idea of this grain boundary stress field. So this plot here is a little bit unusual, but what we're showing here is the colors are the stress field of the grain boundary resolved onto either the incoming or the outgoing actual slip system. And so you can see that there's both regions of positive and actual negative type of behavior, but our green dislocation, which is the embryos that we're trying to form, all of these embryos are aligned periodically with the stress field of the grain boundary, showing that the stress field matters in terms of how the transmission process takes place. The other thing that we can do is we can look down on the grain boundary. So what I'm showing you here is looking directly down perpendicular to the grain boundary. Each of these orange lines or orange or red lines here, these are the positions of our wedge disclination dipole. So this is a very zoomed out view of our grain boundary. And all of these blue lines here, light blue lines here, is the motion of our residual dislocation on the grain boundary under the application of our actual stress field. And what we see is that the motion of our residual dislocation is influenced by the presence of the stress field associated with the grain boundary. So sometimes they have very small cusps, but other times I get these long threading dislocations that are essentially stuck or aligned with the stress field associated with the disclination dipoles. And so ultimately we were motivated by this type of configuration here. And what we wanted to do is we wanted to first say, ask the question, is this a plausible set of mechanisms on there? Is basically DDD is this back here giving us realistic type of evolution of what the actual residual dislocation looks like? So we did some atomistic simulations to kind of explore this. And so we picked the same grain boundary, although we picked on actual number of grain boundaries. This is one of the ones that we study on here. We set up an atomistic model, so it's a fully three-dimensional atomistic model. We have a dislocation loop in our atomistic model, and we apply a shear stress that expands this loop until it interacts with the grain boundary. And then what we did is we looked at, again, the same type of view where we're looking downward on the grain boundary, and we wanted to look at what is the evolution of the absorbed dislocation content that exists basically within the grain boundary. This slip trace here, this is where the dislocation loop interacts three-dimensionally with the interface. And what you're seeing here, this kind of bowed out section here, this is the dislocation moving on the grain boundary under the application of the state of stress that we have. So we see some kind of qualitative features, but we actually wanted to basically analyze this. And so we did an atomic Nye tensor analysis, so that basically analyzes the environment around every atom in our system. We did an actual singular value decomposition because this comes up with a tensor. And what that allows us to do is extract a vector that describes the Berger's vector for the dislocation and a vector that describes, basically line direction for the dislocation. And so what we find is that the Berger's vector for the dislocations are all pointed in a common direction. So you can identify screw versus edge components, and the line directions are all pointed in this actual counterclockwise direction. And so this was in agreement with what we saw from our discrete dislocation dynamic simulations. We saw the same type of features of a consistent line direction and orientation of screw versus edge components in our gliding actual residual on here. So this idea of these threading dislocations based on the stress field of the interface seems to be fairly basically plausible, and it leaves Berger's vector content at these actual wedge disclination dipoles. So we took that idea and we built an initial model for this. So this is what we showed a couple of slides ago. We made the assumption that we have continued deposition and continued basically transmission of our dislocation. And eventually that basically results in this, where some of the disclination dipoles have been influenced by the residual that has essentially glided on the actual grain boundary. So you get these elongated residuals localized near our wedge disclination dipoles. So this was our initial model for how the disrupted grain boundary looks like. Then we did a little bit of math with regard to the dislocations. We made the assumption that the residual dislocation broke into both a climb and an actual glide component, and you can do the math on that. And then we ignored the glide component, and we said that we're going to incorporate the climb component, because the actual climb component is not mobile, on there in with the actual disclination dipoles. And so we end up with these wedge disclination dipole dislocation complexes. And this actual superposition describes, or we used as the stress field of a disordered or disrupted actual grain boundary on here. So if we do this, we can measure the state of stress now, or basically around our grain boundary. So this is grain 1, this is grain 2. Again, this is the stress resolved onto the incoming or outgoing basically slip plane due to the actual dislocation. If we take some arbitrary distance from the grain boundary, we can plot the profile of that stress as a function of distance from left to right along the grain boundary. Our equilibrium model has a very short range stress field. So the stress field essentially looks like 0 here, although it's not precisely 0. It's just very, very, very small at a distance of 40 nanometers, basically away from the interface. But because we have distorted or disrupted some of these disclination dipoles, now we get long range features. We have stresses that are on the order of 10 to 30 megapascals at a distance of 40 nanometers away from the grain boundary. We have longer range stress fields. And when we do our basically transmission, when we send another dislocation in our discrete dislocation dynamic simulations, what we find is that the nucleation or the transmission of our dislocation occurs preferentially where the long-range stress fields essentially are. So the disrupted grain boundary plays an important role in the transmission process. And so you can see it a couple of different examples here. So these disrupted grain boundary regions provide for sites for preferential slip actual propagation on there. What we found is that this overall critical transmission stress for actual slip transmission does basically slightly decrease on here. I'll get much more into this in an actual second. So what we wanted to do then is we wanted to think about a more generalized model, because one of the fundamental assumptions that we started with in the actual prior simulations is that I'm just going to arbitrarily influence a couple of my actual disclination dipoles on there. We want to develop a much better way to do this. So we wanted to understand the evolution of the stress fields due to the absorption of a lot of residual dislocations during our dislocation transmission process. So we wanted to be able to think about a problem like this, where I have, say, a Frank Reed source that's nucleating lots of dislocations, and they, one after another, start to interact with the actual grain boundary. And so based on our model here, with once the first one basically transmits, we end up with an actual residual on the actual grain boundary. But then, and we talked about the actual threading of that motivated by our atomistic simulations. But once the second one gets there, we're going to have additional, basically residual Burgers vector content at the interface. We're going to have twice as much on there. And so again, you can think about adding to the actual residual content that exists at the actual grain boundary in actual superposition type of sense. So again, thinking about how to do this computationally, we've got a couple of requirements. We want to account for the time increment in between arriving dislocation loops. We have to consider the expansion of the slip trace, the expansion of the line along the grain boundary that the dislocations interact with, because even if the second one's coming in, the first one is still expanding, basically along the interface. And then third, we want to consider the incorporation of multiple residual dislocation components. So there's 2 times B res or N times B res based on the number of dislocations that we essentially have. And so we did this we basically included all 3 requirements. Now, for the time for dislocation loop nucleation, we didn't do anything new. We just borrowed some models from the actual literature that were basically presented by actual Steiff and Clifton for if you have a Frank Reed source, what is the time associated with nucleation of dislocations in that Frank Reed source based on the magnitude of the shear stress in the system. Second, for looking at the expansion of loops along the slip trace, ultimately we want to know this L, how much of the grain boundary is being interacted with the first dislocation at the time that the second dislocation arrives. And basically vice versa, when the third dislocation arrives, how much is the first and the second being interacted? So this is just geometry. It's fairly ugly geometry, but it's just geometry. So we can go through and we can derive an expression for this. And then most importantly, we make the assumption that the glide residuals are really fast. They get out of the way, and that truly is an assumption on there. And we incorporate the rest of the residuals at the wedge disclination dipole. So every wedge disclination dipole within this slip trace length is influenced by the residual dislocation that has been left over at the actual grain boundary. And so we could look at the characteristics associated with this. So again, imagine a slip plane, imagine dislocations arriving at the interface. And so we can do the math for this particular grain boundary here. And ultimately what happens is we can plot the region of the grain boundary that is disrupted by the presence of prior dislocation transmission. So this is the distance along the grain boundary versus number of absorbed dislocations. So after the first dislocation goes through, 1 on there. And it's disrupted over a length L calculated based on the time it takes for the next dislocation to actually get there. If we go forward in time, all of a sudden we have a much larger region of our grain boundary that is disrupted by the transmission of dislocations through the actual grain boundary, the actual deposition of the residuals that are actually left over there. So we get this buildup of absorbed, basically Burgers vector content. And what this influences, and I'll show more on this in a second, is this kind of buildup influences the magnitudes of both the negative and the positive stresses on the actual transmission slip system. So the stresses that are pushing out and the stresses that are trying to pull back as it's an actual periodic system. All right, so we calculated the critical resolve transmission stress for different absorbed contents of basically dislocations. And so we did this for a number of different grain boundaries. I'm just going to show two examples here. The first is a sigma, it's basically 627 grain boundary. So it's a 32.47 degree misorientation. And the x-axis here is the density of absorbed basically grain boundary dislocations on there. And the y-axis here is the driving stress ratio. So 1 here is I've got no absorbed basically dislocation content. This is my pristine interface that has a stress field. And ultimately, it required 564 megapascals to push something through that pristine interface on there. But as I add dislocation content, you can see that we get this decrease in the critical transmission stress necessary to transmit a dislocation through that grain boundary. In fact, we get a fairly sizable decrease on the order of about 40% for this particular grain boundary. So that means that these stresses are now on the order of a couple of hundred megapascals. So they're very realistic with regard to stresses that could exist at individual grain boundaries, or could be basically actual driving dislocations. Did this for a different boundary. This is a sigma 123 boundary. It's a 53.60 basically degree misorientation. Again, in this case, our pristine boundary only required 326 megapascals to essentially push that actual dislocation or transmit that dislocation through the interface. And we end up with almost a 70% decrease based on the density of absorbed dislocations at this particular boundary here. So again, we're getting down to hundreds of megapascals, maybe even about 100 megapascals in this case, to describe or for the actual critical stress necessary to transmit a dislocation basically through the interface. So we see this actual softening type of behavior. All of these actual critical stresses are comparable to experimental observations for the magnitudes of stresses existing on dislocations. And then although I'm not showing it here, we still have the same idea that the actual dislocations preferentially propagate through the most disrupted, basically, grain boundary region on there. They're not propagating away from the region that we're essentially disrupting based on prior dislocation transmission. All right, so we looked at analysis of slip propagation through these boundaries. Ultimately, this is kind of an obtuse view of our grain boundary. And so we can see the bowing out. So each of these lines essentially represents the actual positions of the wedge dislocation complexes. We can see the bowing out of our actual transmission embryos, and we see the individual residual dislocations on here. They also bow out within the grain boundary plane. And then when transmission finally occurs, it's actually an unpinning process between the bowed out basically residuals and the bowed out basically transmission embryos here. And so I don't think this is really a concept that's very appreciated in the literature. Most people talk about the bow out of the dislocation that's being transmitted, but we also have a bow out of the residual dislocation left behind on the interface. And ultimately, when it finally snaps and starts to propagate into the transmission grain, we find it's because of the unpinning of those two things. And so this softening behavior is related to the change in the resolved shear stress on the transmitted and residual dislocations in these regions. And so we can measure this. So this is the actual grain boundary resolved shear stress as a function of density of absorbed actual dislocations. And so we get an increase in the outgoing driving stress. We get a decrease in this actual, well, actually, this is an increase in the negative binding stress. So the actual binding stress also becomes stronger on there. But because it has a very periodic pattern, the interplay between this pattern and the externally applied stress that you essentially have is what really causes the actual transmission of the dislocation. So these driving stresses for actual residual dislocation motion increase with rho ABS, and it's this interplay between the binding and the driving stresses that influences this actual slip propagation process. All right, with that, I want to close just in a couple of slides here on how we are going to thinking about validating all of this. we've been working on computational tools to provide a link between the simulation world and the experimental world. And so we're doing this through an idea of X-ray diffraction. So we've been basically developing computational tools from our DDD models to produce experimentally relevant diffraction patterns. So for those who aren't familiar with X-ray diffraction, basically elastic fields produced by all our dislocations are going to distort the lattice essentially around those dislocations. And that basically distortion of the lattice results in broadening of our X-ray diffraction peaks on there. And so if you think of a stress strain diagram, at the yield stress, all we really have is elastic deformation. So this is typically a shift in the peak. But as I begin to work harden my material here, I end up with a broadening or more broad peak on there due to the increased density of dislocations in my system. And then if I unload down here, I get rid of the elastic part, and all I'm left with is broadening associated with the change in dislocation density. So that means that there's a correlation between dislocation density and broadening of these peaks in an X-ray diffraction profile on there. And we want to calculate this. We want to develop and implement a virtual diffraction algorithm to essentially characterize our actual dislocation microstructures. All right, so what we basically have is we're going to use a kinematic, basically, diffraction approach. So we have a diffraction intensity. It's basically calculated in an actual kinematic domain. So this is an intensity. It has an actual equation associated with it. I'm not going to go through all the details associated with this. But ultimately, one of the really important parts is this P of epsilon L on here. So epsilon L is the average strain measure. And this P ends up being an actual probability distribution function associated with that. And so we can compute elastic strain fields, all of these epsilon L's, in a domain containing dislocation. So if I have a discrete dislocation dynamics model, so this would be maybe what one of my models looks like with a given dislocation density, I can create a grid in my system, and I can calculate the elastic strain caused by the dislocation at all of these individual points on here. So that gives me the elastic strain. I can then generate a PDF of the elastic strain average over what are known as actual correlation distances, L. And so in a schematic sense, if you think of all of my grid that I'm going to calculate this on, I can basically, L is my spacing between my grid. And so I can calculate an average over these 2 points, or an average over these 2 points, or an average over these 2 points, essentially, as I'm going through my system. And that ends up with a basically PDF of the result strain in my system. And the X-ray diffraction profile is proportional to this on there. So what we do is we determine the PDF of epsilon L for different correlation distances. So both single L, double L, basically triple L, for example, in each individual basically crystallographic direction. This gives us a bunch of normalized PDFs that have different basically broadening. So you can see what happens when you increase the L. And what this does is both captures the long-range screening and strain gradient effects on broadening caused by our dislocations. And then once we have this information, we can solve our diffraction intensity equation to generate broadened line profiles. So this is what basically an actual diffraction peak would look like for our actual 111 peak. This is what our 200 peak is. And so we can get a whole profile of diffraction peaks directly from our discrete dislocation dynamic simulations. And this is how we are intending to validate essentially our actual DDD models. Now, the one thing that we've done with this at this time is to develop what we call a data-driven framework to try to predict dislocation densities. And this is some work that we're doing at Los Alamos National Labs. Essentially, we can generate a database of many whole profiles over a range of dislocation densities. And they used basically Gaussian process regression to develop a model to relate the whole profile data to a known dislocation density. If I have the simulation, I know where all the dislocation segments are. I know exactly what my dislocation density actually is. So I can verify the broadening versus that known actual quantity. And so they generated this actual data-driven approach, and they tried to do a prediction versus the true basically comparison over 220 networks in aluminum of the predicted dislocation density compared to the true dislocation density from our simulations. And their actual data-driven actual framework was fairly accurate, plus or minus basically 20%, probably actual 30% or so. But this was a better prediction than using the analytical models that have basically been presented in the actual literature. So it gets good, basically predictive capabilities. So in conclusion, basically showed a couple of things today, looked at a model for the evolution of the grain boundary stress field due to multiple dislocation transmission events. And so there are some assumptions in the model, but these assumptions are generally informed by our atomistic simulations on there. We looked at the critical shear stress necessary for slip propagation, and we can show that this can significantly soften based on the slip transmission history on there. This is the first time that this has been shown at the mesoscale with regard to discrete dislocation dynamic simulations. And we show that these actual highly disrupted regions provide the preferential zones for our actual slip propagation, and the grain boundary stresses acting on the transmitted and the residual dislocation collectively contribute to the decrease in the actual critical resolved transmission stress necessary for actual slip propagation. And I think this "and" is something that has really been missing from the literature. Most people think about the stress acting on the transmitted dislocation, not necessarily the residual that's essentially left behind. And then finally, I very quickly basically went through an actual virtual diffraction algorithm to introduce basically how we can calculate strain broadened X-ray diffraction line profiles from simulated dislocation microstructures in our DDD. And we use this algorithm to actually develop this actual data-driven framework to try to predict dislocation densities from our X-ray diffraction peak actual broadening. So with that, these are the 4 journal papers that are kind of either currently under review or basically published that are the actual focus of the stuff that I talked about today. So I'll kind of leave that up on there, and I'm happy to answer any questions either live or in the chat. So,
we start from questions in this room. A student first?
Yeah, student first.
As far as like verifying the results of your model,
Mhm.
is there a reason why you didn't look into using like EBSD or TKD methods to get you like a elastic strain map near a boundary?
So, the actual question was if people cannot. So for the online audiences, in terms of validating the model, why did we or did we not consider basically EBST to look at basically strain maps around the grain boundaries on there? It's something that we would love to do. It's something that we would love to do, something like actual precession electron diffraction to try to get a really highly resolved description of how the stress field looks around an individual grain boundary. But I think the challenge there is that the model is really focused on how the grain boundary stress field evolves with 1 dislocation, 2 dislocation, 3 So setting up a experimental sample to try to isolate individual dislocation responses, I think would be a super, super big challenge basically in order to do that. But we would love to get more information related to how the grain boundary stress field changes due to any type of dislocation transmission process on there. I think the DSUM models are fairly good descriptions of the ground state stress field of the grain boundary, but then how they evolve is I think still an unknown. I mean, we're basically proposing one model based on a number of basically assumptions and actual motivations from atomistics, but getting that experimental validation on how it models, I think, would be really important, and we just haven't got there yet. So.
Maybe I'll piggyback.
Okay.
What kind of spatial resolution would you need for that?
So I'm not an experimentalist. So ultimately, the stress fields. If I go backwards to this, this was our initial model, right? So this was our initial model in terms of understanding. We purposely disrupted a selected set of wedge disclination dipoles, looked at a stress field or how the stress field changes And we looked at a distance of 40 nanometers, essentially, basically away from the grain boundary, because kind of at that point, once the dislocation gets past that point, it really is not coming back to the grain boundary. It's being pushed away, essentially, from that grain boundary. So anything that we can do to get within 10 to 30, basically, nanometers of a grain boundary and really kind of understand what that stress field essentially looks like would be awesome on there. Is that possible?
60 is our limit.
Okay, all right.
Still, but these calculations, they seem to be really sensitive to the grain boundary structure. So if an experimentalist gave you those measurements, but for some kind of arbitrary grain boundary type, would you be able to translate these calculations?
We could certainly take that backwards, essentially.
Okay.
So ultimately, the way that we do these is we're basically injecting one dislocation at a time.
Yeah.
So we're not running a simulation where I have one dislocation and then injecting another one, and they're kind of backed up, because ultimately I have periodic boundary conditions.
Mhm.
And so my residual eventually is going to pass out of the boundary and come back in. And then it's going to influence the evolution that happens when more dislocations come. So we essentially have one event. We said, okay, well, that's the actual grain boundary is going to evolve because of that one event. Now I'm going to apply our model to what happened, and then I'm going to shoot the next one at it, and then I'm going to do this over and over and over again to get this entire curve. So that basically means that if we knew a stress field map from experiments, we could certainly apply that in these systems in the same way that we're applying essentially an analytical model for our stress field in the position associated with the grain boundary in our system. So
That reminds, last question. So I was thinking during your talk, it made me think of these dislocation avalanches that people see. They study a lot in micropillars and single crystals and stuff like that, but they happen in polycrystalline materials too. And what happens is some, weakest link grain will slip and then transfer to the neighboring grain. And then you see these little, polycrystalline avalanches, but they die out eventually.
Okay.
I'm wondering, it makes sense seeing that if the bigger the initial avalanche, the more dislocations are being hit at a grain boundary, the easier it is for it to transfer.
Right.
But why do they die out?
That's an outstanding question. I'm not certain I know the answer to
Okay.
that, but
Really
I mean, ultimately, so kind of going back to the pillar thing with regard to dislocations, basically avalanches, you're creating a whole bunch of dislocations, of course, in that case, because they're typically mostly dislocation free on there. To do that from a DDD standpoint, you would have to have some sort of rule, and people do this for the nucleation of dislocations. And so that's kind of one of the ad hoc rules that would have to be added to this. Now, in this case, ultimately, I could have a Frank Reed source. And if I had an infinitely large model so that the residuals glide away and don't interfere with how they're coming back, then I could have one dislocation after another kind of piling up, and maybe you could maybe potentially explore some of those, because the first one to go through needs the highest level of stress in order to push it through, and then everyone after that is a lower or a softening type of behavior. And so maybe that aspect basically plays a role as they're going through the first grain boundary, the next grain boundary, the next grain boundary after that. So.
Do we have any Zoom questions so far?
Okay,
It's
great.
it's like we're on time.
Right, with positive events. Probably I have a very neat study in the first part. So I'm thinking, can you comment on this wedge disclination model? Is this universal, can apply to any kind of general grain boundary?
That's a great question. So ultimately, our wedge disclination model, I mean, this is kind of the foundation of it. So ultimately, you can think of some orientation, some angle here. And when I have a disruption in my grain boundary, I'm either closing or opening that angle in order to accommodate this additional little feature. And so you can think of it as kind of opening the lattice a little bit and closing the lattice a little bit. So you need to be able to describe the mechanical state of the grain boundary with that type of concept. And so we can certainly do that for basically symmetric tilt boundaries. We can certainly do it with what are known as twist disclinations if I have a twist boundary, although it becomes kind of three-dimensional rather than kind of quasi two-dimensional in actual nature. I could certainly superimpose those type of things. People have also looked at steps in extra grain boundaries, and you can potentially describe the structure of disconnection steps via a properly oriented disclination dipole. But where I think I know where your question is going here is that all of a sudden now, if I have kind of non-equilibrium systems, if I have disruption that is not periodic in some way, is the disclination dipole the right mathematical entity to essentially describe the stress field of that type of system? And I don't know if anybody really knows the answer to that, has really pushed the boundaries on how far these disclination dipoles can be used to describe more generic high angle grain boundaries rather than things that are relatively geometrically special, essentially. And I think that's an important question.
Yeah, so in addition to the, say, high angle, non-equilibrium boundary, if we look at textbook, so you would think the other extreme, the low angle grain boundary, right?
Yeah.
So people try to build up some discrete dislocation. To describe that.
Yes.
So they're actually somehow equivalent. I mean, you
Yes,
think
yes. So you can think of this, you can think of these arms as getting shorter and shorter to the point where you can get a stress field of a single entity, and it basically decomposes to the case of an array of basically edge dislocations on there. And so there is a connectivity between the idea of a disclination dipole, this here, and the idea of a singular dislocation in the limit that you can identify dislocation content within a low angle grain boundary. And so it's fairly this, it's basically the same idea, but applied to high angle cases.
Fantastic. I mean, this is very thought-provoking. I have more questions to ask,
Yeah,
but I
we
mean,
could talk much more.
because of there's technical problems, and Professor Spearot has another next meeting will be in 10 minutes. So probably we have to wrap up here. So thank everyone again, both in room and in Zoom. So this is great talk. Thank you.
Thank you very much, and thank you for coming live.